Okay, so it's great to be here. Thank you for coming early in the morning despite the weather. It will be me talking, but we will be two people or two entities performing. It will be me, and it will be this equation up here. This is the only equation I will show you, but I want you to keep that in mind. But this is the equation that I will be solving over and over and over again. So bear in mind, there's lots of mathematics behind the beautiful pictures that you will be seeing today. Now, the Norrköping Visualization Center was mentioned, and this is just a picture of where I'm from. It's actually warmer in Sweden right now than in Singapore, and the weather is much better. So this is a view where I'm from. Now, the center is a nice place. It's combining basic research on visualization technology together with deployment in a science center setup. So we have everything in-house, from basic research on mathematics, computer science, all the way out to the galleries. And we have lots of education, lots of students, and about 150 people working at the Visualization Center. We have a dome theater. I'm not going to talk about that at all today, but we do have a fully stereoscopic dome theater where we do interesting things. We have a collaboration with the American Museum of Natural History and Carter Emmett, who is here. We do lots of exciting development together in dome theaters. What I will be talking about today is what we're doing in the exhibit area. We are showcasing different aspects of visualization technology, how it can be used to show interesting science projects and do that in an engaging and enticing way. So this is to show what can be seen is our basic exhibit. Now, what I will be talking about today is the challenges. The challenges in going from the basic research, essentially when I work together with the domain experts, when I work with people who are radiologists and try to take their results all the way out to the galleries to do public engagement. Now, what are those challenges? Well, one of them I'm sure many of you are very familiar with is the challenge, what I call the rendering challenge up here now. We are really dealing with people who are of the gaming generation. Now, the gaming generation are people that are very spoiled. They know the latest machines, the latest computers, whatever new high-tech equipment that I have, they have experienced the same. So sometimes when I'm out in the galleries and I'm looking at people and they go and they interact a little bit and say, oh, it's lagging, it's slow, it's spoiled teenagers. And you just want to go up there and hit them in the face and say, hey, this is 20 gigabytes of data that you're looking at, be aware of that. And look at that equation as well. Another thing is the interaction, and as you all know, it has to be very robust, it has to be very accurate, very fast, because also this generation of people, they start interacting. If it doesn't work immediately, they interact a bit more, and then they lose patience and they start hitting until it breaks. We see that over and over again. The last thing here is the storytelling. Now, you have to tell stories that are engaging. And the key is in the data. And what stories can you tell about the data that you're showing? And this is really the main thing that I would like to dwell upon today quite a bit, is to be informative, captivating, but still allowing the visitor to the gallery to be engaged, and still the notion of being an explorer, but still guide them a little bit. And I'll show you examples of that in a little bit. What I will be talking about today is primarily data that comes from CT scanning, and I'm not going to go through lots of details, but I thought it would be interesting for you to see. These are a few pictures of the history of CT scanning. The guy up here, his name is Godfrey Hounsfield. He's the inventor of the CT, the computer tomography, or at least he claims to be the inventor. There are other people who claim to be the inventors too. But he's the one who got the Nobel Prize in 1979 for the invention of computer tomography. Back in those days, you would get very low resolution two-dimensional pictures from CT scanning. Maybe 10 by 10 pixels or something like that, or 64 by 64. This is Godfrey himself in one of the first scanners that was built. Now, a lot of things have happened since then. So this is the machine that I'm using today. This is a Siemens scanner. And don't look at too much of the numbers, but let's look at this one here. 737 millimeters per second is the scan speed. That means that I can put a patient on that table, and it only takes me 2 seconds. I accelerate,
wow.
I go through the hole in 2 seconds. And after 2 seconds, I have 25,000 slices of images, just in 2 seconds. If I start doing time resolved scanning, I can get 5 gigabytes per second out of the machine, and I'll show you that. So here's the full body scan in 2 seconds. 25,000 slices all the way through. 2 seconds. That's too late. If I start using the time result settings, so the next time you come to the hospital, I put the patient in the scanner, it looks like this. So I don't even have to move the table because the texture is so wide. So I get 20 frames per second out of the machine. Medical people, they don't even know how to make use of this yet, because if you have this guy, he has a problem here, this tendon, he's pretty bad. But they don't know how to use this because they're used to putting the knee or the foot in a position and they measure the angles. Now things start moving and they don't know how to use them. So that's lots of research that you need to do. Okay. This is a girl that we put in the scanner. She had a very bad knee. We asked her to bend her knee. No one knew what was wrong with it, but look at the kneecap. Look how it's moving back and forth right there. This is the problem, and they can fix that. So she's good. Now, how do I do this? And this is really the key. And I wanted to give you, before I do some really nice demonstrations on using my Alienware machine here, I wanted to give you a little bit of a flavor for how does this really happen. And here you go. So here are the 25,000 two-dimensional slices of data that I get out of that. All I have is just how much X-rays have been absorbed in each of the points in these images. So I put those back together again, so it becomes like a three-dimensional stack of images that I have in front of me. And my duty, my task, is to turn that into something that looks like this. To extract the structure, extract the content of that three-dimensional data so that I can see something on the screen. How do I do that? Well, it's quite easy. It's only taken me 15 years to figure this out. But here you go. Here's the human eye. Here you have the image plane over here. And there are pixels on the image plane. So for each of those pixels, I shoot a virtual ray through the stack of data. I shoot a ray, and I pick up color contributions, red, green, blue, and opacity, RGB alpha for each of the points. And I put that back together into an RGB alpha value on the pixel. That's the color of the pixel. And then I do that 60 times per second for each of the pixels. And that's why I need very heavy computers. When I started doing this, I paid about $1 million to get one computer that could do this. But now I can do it with graphics processing units that would cost me less than $100. And that's because the kids are playing computer games. So let the kids keep them playing. These are the 3 lines of computer code that are solving that equation that you just saw. So millions and millions and millions of times per second, I'm solving those 3 lines of computer code. So now you've seen everything that I do is those 3 lines of code. And these are the graphics processing units that we have out there. And inside of this machine is the mobile version of this one sitting right in there. This is 25,000 slices of image data. So what's the problem? If I can do this, why do I need to do research on this to be able to deal with the data? Well, the data is too big. I can't fit everything onto the machine. So just to give you a flavor of what I did, was that many years ago, in 2005, 2006, I started thinking, what can I do to reduce the data? There's too much data. Can I reduce it so I can fit it onto the graphics processing unit? Well, I actually can. And the way I do that is that actually reducing the amount of data by saying, here is a lot of empty space in the pictures, but there's actually data over here. There is soft tissue, there is muscles, there is lots of stuff that is not going to contribute with these settings that I have now. So I'm just leaving that out. I'm lowering the resolution in places where I don't need high resolution. And here you can see, here I have a 64:1 compression rate on my data. That's pretty good. So I have 64 gigabytes of data. I can put that onto a graphics processing unit with only 1 gigabyte. Okay. So here's a 200:1, and the error is growing. That's the penalty that I have. And if I have a 400:1, then you can see now everything looks like a bad television broadcast, because now I get low resolution all over the picture. But a 64:1 is what I use most of the time. Now, stepping back to 2006, we had these algorithms. We had done a lot of mathematics on this, and we said, what can we do that will be very exciting as an application? And the biggest data sets that I could get was from what we call the virtual autopsies. And I should say already at this point that I will show you a few images and a few data sets that are from people that have died during tragic circumstances. And it's always with the greatest respect for these people and their relatives that I show the data, but it's technically very interesting, so I'll show them. So here's a scan. So this is a woman, and she's She's full body scan, and I'm just peeling off layer after layer after layer. And so here's this 10 gigabytes of data that I'm just dealing with in real time. What we then did, and this is before the iPad came out on the market, no one knew about touch technology, and we said, let's try to do touch surfaces. You know, and since then, Microsoft and other people have come in, and Apple, of course, as well, has done some things on this. But we took our algorithms, the touch technology, we did some really nice user interface design, and we had a new way of working with medical data. This is a YouTube video that we put out in 2009, and we got several hundred thousands of hits and went almost viral on YouTube, showing how we could utilize those technologies to do real-time interaction with very large data sets on touch surfaces. But why show you a video where I actually have a machine here? So let me see if I can do that. If technology is with me, look at this. Here we go. Yeah, thank you. Just need to touch down a little bit. So now you know everything that's happening in here. 60 times per second I'm solving that equation with those 3 lines of code for every pixel. Now you can see those virtual rays going into the machine, right? Okay. Now, so here's 10 gigabytes of data. And I'm just pushing the button. Here's the touch interface. So this is similar to what we have out in the E3 exhibit, a similar touch table. So here's the body, and now I can start interacting with it with these gestures. So here's 10 gigabytes of data that I'm rotating now, and 25,000 slices of images. And of course what I can do is peel off layer after layer. So here you go. So this particular case here is interesting. It's a virtual autopsy. It's a woman. Let me peel off layer after layer, and let me show you what I have on the inside here. Now here. So this is a traffic accident. I'm very, very proud of this. This is very hard to do with mathematically. I have a virtual flashlight. You see that? I can calculate that. Now, so there's the primary fracture. There are lots of fractures all over the body. And let's just find out the cause of death, because up here is, right up here on the jawbone, there's a fracture. And that fracture turns out to be the key to the cause of death. Now, what I'm going to do is to cut a little bit through the body like this. And then you can see, if I look on the side, right there is the broken neck. So that's the cause of death. Now this is actually the only virtual autopsy case that I would show you, but I have so many data sets with me, and I brought them, and I can maybe even put them on the big table out there so we can look at them out there during the day today and tomorrow if you want to. Now, let me go back and let me just show you one more case that I think could be of interest. Now, let's do this one here. This is a woman. She had an aneurysm in the brain. This is actually quite interesting because, you know, these lines that are coming up here, it looks like a mustache on her. Now, this is actually the x-rays that are bouncing on the fillings of the teeth, because it's hard to do x-ray on teeth with fillings. Now, let me peel off the layers. Down to here, you can see this is after surgery, so she's still alive and doing well, and we have her permission to show the data. So up here is where the surgeons open up. And let me cut through a little bit here. Side. Wow. Now you can see the interior. Now you can see the beautiful pattern. The theme is pattern today. The pattern of the blood vessels in the brain and the 3D structure, the tree that's growing in here. Now, and also what you're seeing down here is the little metal clip made of silver that they used to tighten up the little vessel that could have burst. And then she would have had a major stroke, but she didn't. So she's fine. Okay. Now, let me go back. Now, we scientists, we publish papers, and we think that's the best measure of success. We count citations, and maybe I get a few hundred people reading one paper. But when you do things like this and you put it out there, you get a lot of attention by media as well. So my wife, she's a social scientist, and she's here in Singapore now. And she said, now you have finally done something that's okay. Because the Economist, that's the only thing that she counts. So we got a lot of attention. We turned the whole thing into a medical product that's out on the market. We have 300 installations worldwide. It's primarily used for medical teaching. Teaching medical students about anatomy, but also for surgical planning and things like that out on the hospitals. And we're hoping that there will be a few installations here in Singapore in a while. And when it's out in the hospital, it looks like this. It's a very nice setup then for teaching surfaces. Yeah. But that's not what I'm going to talk about. What I'm going to talk about is this. I don't know how much you're into the royal families, but this is the Swedish crown princess. Her father gave me the medal a few years ago. So this is the crown princess, and she's trying out a table. This is the radiologist that I'm working with, and this is Thomas, my student over here. This is the Prince Daniel. He used to be her personal trainer, by the way. Shame on her. Okay, now, so the reason why this picture is so important is that she was going to Shanghai to the expo, the industrial expo in Shanghai in 2010, and she said, you have to bring something to the expo that will showcase Swedish technology, and this is the best I've seen so far, she said. So bring this. So we did. So here's a picture from Shanghai in 2010. We had thousands and thousands of people waiting outside. You know, I was in Shanghai earlier this year and I realized that 1,000 people in Shanghai is not very much. But at the time I was very impressed. But one of the things that impressed me the most was the fact that it was not only grown-ups that came, it was also the children. So children were very interested in exploring difficult data sets, you know, virtual autopsies, you know, things that you would think that they were afraid of, but no, they were very engaged in this. And luckily, very soon after this, we started talking to people from here. So it's wonderful to be here, because one of the first places where we actually put one of these tables out in the public place was actually here. So thank you very much for that. But we also moved on to other places, and there's a long list of various installations worldwide that's now using this technology. The Field Museum in Chicago, you can look at Peruvian mummies. But the interesting thing, and this is where my story takes off to the next level, where I think it gets really exciting. This is when you start talking to the big museums that have their own artifacts. The Natural History Museum in London is one of those. Now, the museum, they have enormous galleries with all sorts of things that you can ever imagine. If you're into rocks, this is the place to go. But what they also have is down in the basement, they have millions of artifacts that they have collected from all over the world. And they never make it to the galleries. And some of those are quite interesting. And we can scan them using all sorts of imaging modalities, not only CT scans, but all sorts of other things. So, courtesy of the Natural History Museum, I can show you some of those very exciting data sets today. So, let's see. Let me start by bringing up this one. This is an African beefly. Remember the days when you would go to the museum and they would bring you the insect part of the museum, and you were going, yeah, right, that's very boring because the insects are pegged to boards. Now we scan them. And now you can tell exciting stories. Here's an African beefly. Look at this. Look at the resolution of this guy. And here I can tell the stories, you know. I had little info tags. I'm telling the story. You're free to explore, but I'm telling the story, and I'm giving you clues to what you are supposed to explore next. So you have full freedom. It's the same data set as the scientists are working with. You can even virtually dissect the insect and look at it from the inside if you want to, like this. And you can use the magical flashlight to shine through it like this. Change the settings, everything like that. Look at the hollow spaces inside of it. So it becomes a very exciting process of developing, you know, the skills of exploring, just like being a scientist yourself. Okay. I have so many data sets, and I only have 30 minutes. But I can't resist to show you at least a few of these. Now, so this one I think is one of my favorites. This is a small piece of amber. So 20 million years ago, before there were humans on Earth, a small gecko lizard got stuck in tree sap, and it turned into amber. This is only 5 centimeters. So here it is, CT scanned. And just turning it around, you can see the shadow of the gecko lizard there. And magically changing my settings, there it is. That's the beautiful pattern of the skin of the lizard. Extracted out. But the bone structure is a little bit there, but all the soft tissue is gone. So then you might ask yourself, how did I do that? How did I recreate, you know, the skin, the scales on the lizard? Well, there's a trick to that. So here's the piece of amber. Now look at this. Cutting into it, and there you go. So what I'm visualizing is actually the imprint of the scales in the amber. Okay. What else do I have? Well, I promised in my abstract that I would show it the Martian meteorite, but here it is. So in 2011, a meteorite landed on Earth, and we know that it came from Mars because of its trajectory and also its chemical composition. So we can scan that, and here it is. So it's a piece of rock. Here's the chemical composition that you can visualize, and you can explore that. The most exciting thing about it is that if you look at the interior, there's a little pocket of air inside. That could potentially be a Martian atmosphere. A Martian atmosphere from a few billion years ago. So this could give you the clue to whether there was life on Mars or not. Or indeed if we came from Mars. If we were. So, as I said, I have so many different things here. The penguin and so on. We'll see if I get more time towards the end. Now, if you talk to the Natural History Museum in London, they have 5 million visitors per year. There's another museum, the British Museum, they have 8 million visitors per year. And they have two things that they're very proud of. Well, there are many things that they're proud of, but the two most precious items that they have is the Rosetta Stone. And then they have a mummy called the Gobelin Man. Gobelin Man is 5,500 years old. He's pre-dynastic. He was found down in southern Egypt, close to the border to Sudan. And he's been at the museum for about 100 years. So we took Gobelin Man. They knew very little about him. We took him to one of the hospitals in London. And we CT scanned him in the scan, not quite as good as ours, but it was okay. And this is one of the first sessions that we had. So this is a guy here, let's see, this is Neil Spencer. He's the keeper of Egyptology at the British Museum. He's an Irish wizard. This guy here has the title that I would like to have. He's Daniel Antoine. He's a physical anthropologist, head of human remains. He's the mummy guy. And there are some people that are working with us and some media. Now, they're very excited about something here. So what is it that they're so excited about? Let me show you. Now, they're very excited about this thing here. So thank you, British Museum. Now I'm going to bring you the Gobelin Man here. So here it is, 5,500 years ago. Now look at this guy here. Now I'm going to cut a little bit from above. You can see the brain is still there. So this is pre-dynastic, is before the traditional mummification process. It's just dried in the sand. And there's lots and lots of dried tissue on the inside. Now, one of the things that they were so curious about was this fold here, on this little left shoulder blade here, there's a damage up here. So they were wondering, is it just the way that he ended up? Did the shoulder blade dry that way? Or did something happen to him? All they knew was that he's a young male. But with the help of the virtual autopsy, we could cut him open. You can look from the inside, and here you go. Right there. Oops, the light source, let me show you this thing here. Right there. The rib cage is broken. So there's a fracture on the ribs, and if I show you that's pretty easy to see. Okay, there you go. Right there. So it turns out that he was stabbed in the back. And we even found a knife close by that we scanned, and it matched the wound. So this is a 5,500-year-old murder mystery that we found. We found the weapon. We did not find the murderer. And this installation is still there at the British Museum. So let me show you a few facts about it, because I think this could be of interest to you to know a little bit about this. And so here's a lot of media attention. I like this murder at the British Museum. But perhaps this is maybe the most interesting slide that I have for some of you today. Now, we did an evaluation of this installation at the museum. And of course, one of the things that they were afraid of was that digital media would attract attention away from the physical subject. This is what you hear from curators at the museum all the time. As soon as you come with the digital media thing, they go, no, we don't want digital things because we want the physical thing, we want the real thing. What happened? We had 6 months in the gallery, one person sitting there timing the visitors. Every single interaction, every person coming in, logging them, what did they do? We had 95% utilization of the table. So 95% of the opening hours, someone was interacting with Gobelin Man. the time that people spent in the gallery increased by a factor of 3. And they were very impressed by this number. The time that they spent studying the physical subject, actually looking at Ynnerman, doubled. Because they would typically interact with the table, look at the table, figure something else, and then go look at the mummy, and then go back and forth all the time. And there was always a queue, and lots of kids around the table as well. So one of the things that we did was that we logged the interactions, and now we're doing an analysis. We did change a few things in the interaction to make it easier to enable multi-users, like rotations, auto-rotations, cut plates, things like that. But it turns out, so yeah. So that was very interesting. Now, the last thing that I'm going to show you is perhaps the most beautiful mummy scan that we have done. This is Neswayu, and this is indeed the mummy that you can explore yourself here at the Science Center in Singapore. Now, the story about this guy is that he's about 2,000 years old. He's resting at the museum, the Mediterranean Museum in Stockholm. So what we did was, let's go beyond just only doing CT scanning and do surface scanning and all sorts of scans that we can possibly do to put together a virtual digital copy of the mummy. So the first thing we did was transporting him. This is our scanner, the one that I showed you before. Here are some people from the museum, here's the radiology nurse, and there is our interaction designer over there. And now you can see the speed of the scan. So putting him on the table, and just a few minutes later, we're just pushing it through in a few seconds. Now we're doing an extremely high resolution scan, so it takes a little bit more than 2 seconds. But this is what we do. And we're done. We have 25 to 30,000 slices of image data from the mummy. What we did after that was also doing surface scanning using laser scanning, very high resolution scans. We did this together with the company Autodesk. We did photogrammetry, high dynamic range photography, all possible angles of the various layers of the sarcophagus, the coffins, all the layers in between. And eventually we did a huge data fusion project to put everything back together again. And now I should be able to show you that. And of course what I have to do is bring up, and now you can see that I'm running Windows. Microsoft. There we go. So here's Neswayu. Now it takes a little while to load the data for Neswayu. It's a very big mummy, so it's 30 gigabytes of computer tomography data, and then another 20 to 30 gigabytes of image data that I'm loading now. And nothing has been pre-processed, it's just the raw data that's sitting in here. And thanks to that NVIDIA GPU 980 mobile version, consuming about 13 kilograms that I have to carry around all over the world. But here he is, so here's Neswayu. And look at him. It's better on my screen, I think, but look at the details and look at the patterns in this one here. This is the outer layer that we're looking at now. And now I'm going to peel off layer after layer. So here's the inner coffin. And I have to show off, being a computer scientist, I have to show off the lights. Look at this, this is hard to do. Look at the speed of the light. So this is the next layer. Here's the cartonnage, it's basically papyrus. And this is the beauty of patterns today. Look at this. 2,000 years ago, this is. Just getting the notion of exploring this, rotating it and touching it is sort of magic. So don't miss that experience out there. And next layer is the wrapping. Here they did a biopsy in the 1960s because the organ bag is right inside of here, so they want to get some tissue samples out of it as well. And eventually I find the body. Now it's very hard to do nice imagery of very dry human tissue because X-ray absorption is about the same for dried bone, dried skin, dried organs, everything. So this is perhaps the best we can do. Okay, so here it is. Now the area that I found very interesting is of course up here where there's all the jewelry. Look at this. So what we tried to do was to extract that a little bit more over here. And eventually what we did, and I don't have the time to talk you through all the details of this, but perhaps I do actually here. So here you can see, so this is the part of the body where we found the extra high resolution scans, and you can see all the details in here. And again, telling the story, so we're helping the users to actually explore a little bit about the content. Okay, now, of course, if you have an area like that, the head is exciting too, but if you have an area like that where you find some interesting jewelry, you do the extreme, most high resolution scan you can ever imagine. So here it is. And here you can see the shape of something that looks like a bird. And with a bit of mathematics, and I always tell kids that come and look at this, remember that this is mathematics. Behind every single thing that I do, there's thousands of lines of mathematics. I can do this. So I clean up the data. And out from a mummy that has never been unwrapped, I can extract the jewelry. I get 3D representations. So now I can interact with the falcon from a mummy that has never been unwrapped, because of course we are not allowed to unwrap mummies anymore. They used to do that in the past. And these days, if you have a 3D representation, of course you can 3D print it. So here it is. 3D. This is the only one that I brought, so I'll pass it around. According to Egyptology, if you mention the name of the mummy when you hold an artifact from it, it will bring happiness to the mummy. So say that's why you when you touch it. Okay. Now, how do we do this? So here's the 3D printer. We print it in plastic. These days you can print directly. I mean, it's standard procedure these days. You can print metal pieces directly. The one that we made is, we made this cast here, and it's made out of bronze and then it's plated with gold. You know that it's gold because of the X-ray spectrum, so we're really sure that there's gold inside of the magnet. And here it is. But eventually, perhaps this picture is what I think is really the content of my whole presentation, is that by taking this very basic research on mathematics, computer science, and bringing it all the way to the gallery, as a professor coming into the gallery saying, hey, these kids are getting excited by the mathematics that I did 5 years ago. And that's a very rewarding experience, much better than citations to papers. Now, what are we doing now? Just to give you a flavor for where we're heading. Now, we are developing a piece of software that will enable people that have their own data to just take our software, download it, get one of these tables, and woof, tell the stories immediately. And if you're interested in talking to me about this process, or what we call the science portal, please approach me at any point during the day. So, a few conclusions. Now, what I think is happening is that the magic that I am creating by putting the real data out there is this connection between reality and virtuality in some sense. You really become the explorer. There's this stuff in between is not really there anymore. And if you do it in a nice way, with a nice user interface, you can maintain that magic, the magic of touching something that's almost real, bringing you closer to the real thing. So we deal with a new generation, and they really want to do this stuff, and it's very exciting. Now, so what's happening? I think that visualization is really, we're going through this revolution. You will see, and you were beginning to see, we were perhaps the first ones that started out in this, but now there are many other people that are doing this, and it's happening all over the world. That visualization, visual media, interactivity is really the primary means of communicating complex phenomena, interesting science, and do that in a very engaging way. But it's not done. Because the visitors are not patient, the curators are not good at doing these things, and the software is not there. So there's a lot of research that needs to be done, and lots of opportunities for different companies to do this. My last slide that I want to put up, everything that I've shown you, of course, I'm the director of the center. I didn't do everything myself, so here's the name of the people that did most of the work and all the beautiful pictures that you've seen today. So my great thank you to all these people that made it possible. And finally, also, our little spin-off company that is now this installation here. Thank you very much.